Welcome back. I couldn't stand to be inside any longer on such an incredible day. Last time we discussed how ions get together to form ionic compounds, how you have a metal that will give away electrons to a nonmetal, making the metal positive and the nonmetal negative. And then the metals get together with the nonmetals and make compounds. So today we're going to talk about some of the properties that we see in ionic compounds. Stick around. In order to make one of these ionic compounds, the charges from the metals and the nonmetals that get together have to be in balance. There has to be a zero net charge. So we could kind of think of this in terms of, say, a teeter-totter or a balance. On one side you have the charges for the metals, and on the other side you have the charges for the nonmetals. The two sets of charges have to balance each other in order to have zero net charge. For example, let's say we want to have a compound of aluminum and oxygen. Aluminum oxide. Aluminum has a +3 charge. It's in group 13. The oxide ion has a -2 charge. It's in group 16. If I begin by having one aluminum ion on the metal side and one oxide ion on the nonmetal side, I don't have a balance, do I? The same can be said if I add another oxide to the nonmetal side. I still don't have balance, do I? It's not until I place 2 aluminum ions on the metal side and 3 oxide ions on the nonmetal side that I have balance. That's when I have a zero net charge. So I know that my compound between aluminum and oxygen has to be Al2O3, aluminum oxide. You get it? Whenever you have one of these ionic compounds, you don't just have one set of them, you have a lot of sets of them. Many of these metal and nonmetal ions coming together. These ions are packed together in clusters in regular repeating patterns, a crystalline pattern. This pattern balances the forces of attraction between the positive and negative ions. For example, if we're talking about sodium and chloride, table salt, the sodium ions will be surrounded by the chloride ions, and the chloride ions will be surrounded by the sodium ions. That gives balance, but it also gives a nice crystalline structure. In this case, a cubic structure. That's why if you've ever seen rock salt, you notice that the rock salt takes on a cubic shape, doesn't it? It's because of the placement of sodium ions and chloride ions. So these ionic crystals are highly organized with consistent patterns throughout. Those strong attractive forces between positive ions and negative ions and their arrangement gives us what we call a crystal lattice structure. Simply put, a crystal lattice is a three-dimensional geometric arrangement of particles. Each positive ion is surrounded by negative ions, and each negative ion is surrounded by positive ions. It's interesting to note that they don't all look like sodium chloride. They don't all have a cube shape. Some of them have different shapes because of the different ratios of metal to nonmetal involved in that ionic compound. Tell you what though, let's go inside and talk about some of the physical properties of these ionic compounds. Now, really, a lot of the physical properties that we see with ionic compounds have to do with how strongly they are bound together by those positive and negative ions. As it turns out, most of these ionic crystals are pretty hard and rigid. You might even say brittle. Now, this is because of those strong attractive forces that hold those ions in that crystal lattice structure. But they are indeed brittle with those attractive forces. When we apply an external force to these ionic crystals, the crystal doesn't bend, but rather it breaks apart pretty readily. The reason for this has to do with the arrangement of those ions and how they're rearranged when you apply an external force. Let's use sodium chloride as an example again. You can see the arrangement of ions we have before any kind of external force is applied. But when we do apply that force, the rearrangement involves pushing like-charged ions next to each other. The result is a repulsion, isn't there? And that repulsive force causes that ion to separate rather quickly. So those repulsive forces break apart the crystal. Now the ionic bonds in these crystals are relatively strong. So because of that, ionic compounds usually require a large amount of energy to break those bonds apart. That translates into high melting points and high boiling points. Since ionic compounds involve the transfer of electrons, that means they have the potential to be a conductor of electricity. But whether or not that ionic compound will be able to conduct electricity has to do with the arrangement of those ions. If the ions are locked in position, like they are here in this solid form, we can see that no electricity is flowing through. It's because those ions are in a fixed position, locked in that crystal lattice structure. However, that situation changes when the ionic solid is melted or it's dissolved in a liquid solution, like so. I placed a little water in the bowl with the ionic solid, and you'll notice now it conducts electricity. Electrodes out, electrodes in. You see that? Before, the ions were locked in their position in that crystal lattice structure, but now those ions are free to move, and in doing so, they're free to conduct electric current. Any ionic compound that can conduct electricity when it's in an aqueous solution is called an electrolyte. You've probably heard that term before with certain sports drinks and so forth, but simply put, it's a solution that's able to conduct electric current. In any chemical reaction, you've got energy that's either being absorbed or released in the process. If energy is absorbed during the process of that reaction, we call that endothermic. But if energy is released, we call that exothermic. When ionic compounds are formed from positive ions and negative ions coming together, it's always exothermic. That attraction between the positive ion and negative ion is a more stable situation than when they're apart from one another. To pull those ions apart requires energy being placed into the system. You have to introduce energy to make that happen. So, the pulling apart of ions is an endothermic situation. Energy has to be absorbed in order for that to happen. So since those ions are arranged in a crystal lattice, the energy that's required to separate 1 mole of that ionic compound is called lattice energy. The greater amount of lattice energy required means there's a stronger force of attraction there. And some ions are stronger than others. Now, the closer those ions are to each other, the stronger the attractive force is going to be. Because of that, typically we see that smaller ions have stronger lattice energy. They're more closely spaced together, which gives what we call strong inter-ionic attraction. Fancy term that just means they're more attracted the closer they are together. Because of that, they have higher lattice energies. For example, let's compare the two compounds lithium fluoride and sodium fluoride. Same anion involved, but different cations. You'll notice that the lattice energy of lithium fluoride is larger than that of sodium fluoride. The reason is that lithium is smaller, so those attractive forces can be closer together in lithium fluoride than they can be for sodium fluoride. Thus, the lithium fluoride has higher lattice energy. So the smaller the ion, the more concentrated the charge, we'll say, the higher the lattice energy. We also find that the magnitude of the charges has a lot to do with lattice energy as well. We see, for example, that magnesium oxide has a lot more lattice energy than lithium fluoride does, even though lithium fluoride is dealing with smaller ions. The reason is that magnesium has a higher magnitude of charge than lithium does, and oxide has a higher magnitude of charge than fluoride does. Magnesium has a +2 charge, and oxide has a -2 charge. So an ionic bond that's formed from the attraction of ions with larger positive or larger negative charges will give greater lattice energy. The lattice energy of aluminum oxide would be even greater than magnesium oxide, since aluminum has a +3 charge compared to magnesium's +2 charge. Again, the greater positive or negative charge you have, the greater the lattice energy. That's all we're doing for this video. We discussed the properties of ionic compounds today, and we started with the physical structure, how we can have a crystal lattice structure for our ionic compounds. With that, we discussed how the attractive forces between these ions are strong enough to give us high boiling points and high melting points. And we also mentioned how these ionic compounds are often electrolytes, how they're able to conduct electricity when they're placed in a solution. Finally, we discussed the concept of lattice energy, because the closer proximity of ion to ion gives greater attractive force, and also how a greater magnitude of charge can give us greater lattice energy as well. Hope it's been helpful to you. If I can answer any questions for you, let me know. Until next time, God bless.